Welcome to our NPTEL courses on the power quality improvement technique. We are discussing about the grid connected voltage source converter. We have discussed about the outer voltage control loop in a DQ frame of reference. We are going to discuss the inner current control loop and also the phase lock loop, that is one of the important aspect in our voltage source converter in a grid connected operation. So, let us talk about the current control. So, since we have not connected any resistance, so for sake of operation, and it has been, we have shown in the voltage mode, because there is a lump resistance that is been represented there, we will neglect the resistance in our previous equations of equation 5. Please refer our previous lectures. So, what happened? So, you got L di dq, and there is a little simplifications, just R into I d is actually omitted, considering that resistance part is quite less. So, you got V d minus the d axis component of this converter voltage plus omega L I q. Similarly, you have the q axis component, rate of change of q axis component with the inductor equal to the q axis component of the grid, q axis component of the voltage of the converter minus omega L I d. The decoupling term of this current derivative, this is basically the current derivative, can be eliminated assuming a decoupled controller using the PI controller as follows. So, this is something, please understand that we wanted to, this is one of the problem. We want to control basic purpose of our DQ control is to operate, it was come from the induction machine operations. Essentially, you can directly, we can control the d axis component, that is nothing but generally the voltage component and the flux component, and in that will be independent to each other. So, speed and the torque can be controlled independently, that was the main motive of the DQ. But while doing that, here we wanted to have a real axis component and the reactive axis component separately. But unfortunately, there is a coupling term in between. How to get rid of this coupling term, that is a challenge. So, we require to decouple for the independent control, and we are saying that it can be achieved by the PI controller. So, this is one of the technique. So, VCD we can write as Kp plus Ki, this is a PI controller, into Id minus Id star, which we have shown in the figure 2 in your previous class, plus omega Li plus the grid voltage at the d axis. Similarly, the Vq equal to minus Kp plus Ki by S, Iq minus Iq star minus Iq plus omega Lid plus V GQ. So, you get both the term, and thus you can see that how you can segregate this term in our next slide. So, now this is a equation 6. So, you substitute here this term and this term, and thus subsequently the equation which you will get is the equation 8 with little rearrangement. So, ultimately what you get, it is Id q equal to Kp plus Ki by S, Id star minus Id, where Id is the reference, please go back to our second slides of previous class. There we have discussed the principle of operation of the grid connected inverter. Thereafter, L dq dt equal to Kp plus Ki by S, similarly in the Q minus Q star. With this, we can say that the control of the d axis current is decoupled with the q axis current and vice versa, just choosing a proper PI controller, and PI controller, it is easier to operate in the DQ mode because this quantity looks like DC. So, there is no problem with the bandwidth. So, how this block diagram it has been represented. So, it is a voltage. So, d axis component of voltage of the voltage source converter minus Kp plus Ki by S, Id minus Id star minus Id plus Lq plus Gd. Similarly, it is Vcq equal to minus Kp plus Ki by S Iq minus this term, Iq prime Iq star minus Iq minus omega Lid plus Vgq. So, Id star minus Id you can subtract. So, thereafter you feed to this PI controller, this PI controller, and ultimately you have to subtract with this term with the VGD, and ultimately you essentially what you get, it is the reference component of the of this converter voltage in d axis. Similarly, if you have a IQ and IQ star and you subtract, and from the subtractions you get this term, thereafter you subtract with the VGQ, and thus what you get essentially a VQ reference. You convert with the theta ABC to DQ frame, essentially you get the gate voltages for the ABC frame of reference. This is the way to control your grid connected voltage source converter. Now, active and reactive power flow control, that is quite important, because you may be charging the battery. Once you are charging the battery, so you require to have your charging current has to match the thermodynamics of this battery. So, you cannot, so there is a trickle charging mode, there is a constant charging mode, there is a constant voltage charging mode. Essentially, we require to see that if you are putting the more current, then whether it is converted to the heat or the thermodynamics of this battery, it is essentially a chemical process is been enhanced, or you require to send back the power because you have a limited capability from sending back the power from the grid to the grid, or you have a energy surplus. So, you can give that energy which you have a surplus only, but grid itself is an infinite sink if you try to send the power. So, for this reason we require to control the real power, as well as you require to inject the power in a certain power qualities, because you are allowed to inject power at 0.95 power factor, you are not allowed to inject in any power factor, and for this reason we require to control actively the active and the reactive power control. So, complex power is been exchanged because it has a both the component in DQ frame of reference, and that complex power or the apparent power, we can write that it is the 3/2 Vg, that is the voltage dq into IdQ star. So, if you split or the expand, so you got 3/2 Vg plus j Vgq, and you got IdIQ, and thus you got 3/2 Vg plus j Vgq Id minus GIQ From there we can split the real and the reactive part of the power. So, it is 3 by 2 VGD into ID plus VGQ into IQ plus J VGQD minus VGIQ. So, that becomes equation number 9. So, active power transferred here, it is PCC prime equal to 3 by 2 GD into ID plus VGDIQ, that becomes equation number 10. Similarly, this is expressions for the reactive power component, that is 3 by 2 VGQ ID minus VGDIQ. So, this is the equations. So, this is the reactive power required to be transferred, and this is the real power required to be transferred, or the active power required to be transferred. So, what we can say that under steady state conditions, and we assume that these losses are neglected, semiconductor losses are neglected, filter losses are neglected. So, active power exchange at PCC, that is point of common coupling, equal to active power injected into the DC side of the PCC, and thus 3 by 2 the grid voltage into grid current in D axis plus grid voltage and the grid current in Q axis should be equal to the DC power conversion, that is essentially VDC into IDC, and thus IDC value should be equal to 3 by 2 GD into ID plus GQ into IQ by VDC. It means from this DC network, the converter acts as a constant current source of magnitude IDC. So, this is something we can conclude. And moreover, what you can note here, so here the AC network is connected with the voltage source converter. The use of the reference frame enables the decoupled linear control and active reactive component of ID and IQ. So, we can actively control the value of the ID and IQ. So, another interesting entity we have shown several times in Parkes transformation, that ABC to the alpha DQ frame, that U required to generate the theta, and that comes from the phase lock loop or PLN. So, what is PLN and how does it work? That is something we are silent. So, let us discuss about this PLL in the sections here. So, ultimately this is your D axis component and this is your key axis component, and with respect to alpha beta component you got an angle, maybe the rho t, where rho t is greater than theta g, and whereas this is the grid voltage. With grid voltage with the D axis, generally A and D are been aligned, you got a angle theta g. And if this happens, if the rho t is less than theta g, we say that grid voltage is leading. Whereas, if reverse happen, this value is the theta g, this is alpha, and this value is Vg, and this value is the D axis component of the grid voltage, and where rho t is greater than theta g, we call that grid voltage is lagging, and this is called the phase phasor of the in a rotating frame of reference. Now, how we do that? How we will calculate the theta? It is quite simple, what is the expressions of your voltage? Voltage equal to some constant 4.44 thereafter you got flux density plus A into N into F, right, and thereafter the winding constant may be Kw or something. So, what you require to do essentially the frequency, if you integrate, you get the theta, very simple thing. It is so theta is dimensionless. So, it is frequency as a dimension of 1 by t. So, we require to integrate it. So, for the 3 phase 3 wave system, generally we can generate one of the phase by subtracting with the 0. You may not take the one of the phase here. So, here you have any of the phase you can take it and you go for the Parkes transformations, but how you will generate the theta or rho. So, essentially you try to align your A phase of the grid with the D, that is a convention, and ultimately you feed the GQ into the high gain proportional controller, mostly this one. This is called compensator, because after some value, because you know that omega has been limited to some value. So, it cannot be more than, for the 50 hertz cycle we have some kind of tolerance, you know that omega is 314 plus minus 5 hertz or 6 hertz, something like that. So, maybe actually 310 to 320, in between you can keep this band of the proportional band, and but this band is quite steep. So, ultimately it is, if you can see that here, it is generally a 50 degree curve, 45 degree curve. So, now what now you subtract this value, this is essentially a mapping. What is the value of the Q you are getting, you will map it to the frequency ranges to the 310 maybe to 320, considering that 50 hertz and you have around 314 as a midpoint value. So, you subtract with the omega s and whatever is the your generations. So, this is essentially what, very simple, a unit voltage template. So, that has to match and ultimately you integrate the value and it is called a voltage control oscillator, and thus what you will get, this will give the feedback to conversion. If it is matches, then A, and if you go back to the slides, you know, then this will not have a lagging problem. Ultimately this G and this D will march together. This is the purpose of this PLL. So, this DQ frame GDD of T plus J VQ equal to Vg e to the power j omega t theta minus rho. Thereafter, same for the q axis component, thus it will be a sine component, Vgq equal to Vg t sin theta minus rho of t. Similarly, we can write that Vgq is almost equal to Vg equal to theta minus rho by the unit voltage template, that is nothing but a Et. So, the error is Et, so that is the rho of t, Et you multiply with the Vgt, that gives you the q axis voltage and you got a compensator, that is basically maps the voltage into the frequency. So, that error represents the voltage and you subtract with the unit voltage template and you feed it to the integrator, because I told you that frequency, if you integrate you get the theta and ultimately you get the theta. So, this is the way of working principle of the your PLL. So, you got a Vg ABC PLL, you get Vg, you get theta as well as the frequency. So, this is the something you can get from your PLL. Now, once this phase lock loop itself to the grid voltage reaches the steady state. So, that is the oscillation, it will be there initially, and then what happened, that is what I was saying, that rho t equal to g t and omega estimations will be equal to omega of the system. Since you have totally aligned your d axis component to the a axis component, so thus there is no q axis component in the voltage. So, for this reason your GQ value will be 0 and thus your GD value will be equal to GT. So, this is the way it will be converging in case of the PLL. So, going back to the discussions again. So, this is a way of PLL works, but it is it will work when your voltage is healthy. So, if there is a issues with the unbalanced, you got a positive as well as the negative sequence component of the voltage, then you require to do something else to estimate the PLL. So, that will be, if time permits, we will discuss in detail about those PLL, but let us take a elementary example of it and proceed like that. With aligning the d axis converter voltage along the grid voltage, the active power flow of voltage source converter of the PCC, of course, it becomes, that is 2/3 Vg into Id, that is the real part of the component, and the reactive power flow will be equal to Qc, that is equal to 3/2 Gd into Iq. This will be the cross term, voltage will be d axis and current will be q axis. So, we can put it like that, it is power of the converter will be 2/3 V Gd into Id and Qc equal to 2/3 Vgd into Iq. So, this will be the concept. So, let us see that overall block diagram of it, and it is applicable for D StatCom, it is applicable for the active power filter, it is applicable for active rectifier and also solar inverter in case of the microgrid. So, this is all can be tackled into the single block diagram, and this mode of control is called the SRM mode. So, ultimately if you have a real source, then IDC will be sinking. So, assume that you got a real source and you can feed the power to the grid. So, and you are maintaining the value of the VDC here, and this is the converter. Ultimately you got the value of VA, VB, VC, and thereafter you got a inductor, because instantaneous value, because it is a PWM pulses here and here you got a sinusoidal waveform. So, you cannot couple them together, and due to that you require to connect an inductor in between. So, after that this grid current becomes the IAG, similarly IBG, ICG, and this is the detector of this PLL, ultimately theta detector, or you can write the PLL. From these 3 voltages you can detect, and from there you got the theta g, because rho will be equal to theta g whence you have a balance of the system. So, you will convert this voltages and current, because you can see that you have taken 2 voltage and 2 current, because it is a 3 phase 3 wire system, and you know that V A V B V C equal to 0. Similarly, I I B I C equal to 0. So, you got I D G, I Q G, V D G and the V Q G. These are the 4 signals, and ultimately you have a reference Q and you will have a reference VDC. From there you got a difference IQG, and that will be subtracted here with the PI controller, and there is a cross term as I have told you in the previous case. So, it will be multiplied and it will be dealing with the d axis component. Similarly, there will be a d axis component will be multiplied with the IQ and will be dealing with the q axis component. So, it becomes the VQG and this becomes your VDG, and these signals will be fed to the inverter or the converter depending on the mode of operation to the VQ, and it will be converted to the ABC to the DQ frame, and thereafter you have a PWM controller to feed them to track the reference. So, that the whatever the and there will be a different mode of operation. If you find that there is a sag in the DC bus voltage or solenoid DC bus voltage, then this loop comes into the picture. Otherwise, you can see that it is a QG control, and this is applicable mostly in the active power filter or the D-STATCOM operation. This is the SRF method of control of the D-STATCOM or the SRF. So, there is a outer controller, this was the inner controller, and this will control your active power. So, you know that active power PC will be equal to, we will neglect the losses, that is something we require to, if you do the proper total modeling, then you require to take the losses. So, it is PC prime equal to 3 by 2 V GD into ID. Similarly, you have the I max equal to IN. So, what is the maximum value of the ID you are allowed, because you are choosing a devices and device has its maximum current limiting rating, otherwise this protection circuits will come into the picture to stop the operation. And for this reason, this value is that, let us say I max equal to IN. So, you have a PC star minus PC, from there you got a PI. So, you got a I max and ID min, from there you got a ID prime. And similarly, you have a reactive power control, and that is mostly important because this was required for the active rectifier and other mode of operation, but in case of the shunt active power filter or the D-STATCOM, this loop is generally absent. So, active power control, so it is minus 3 by 2 V GD into IQ, and thus IQ max will be definitely it is the square root of this, and from there you will be calculating the IQ star. So, this is something you require to remember this. First calculate the ID star, and thereafter from the power rating we require to calculate the IQ star. So, now we have a DC voltage control. DC bus required to be maintain some voltages, and for this reason we require to have a control. So, it is PC prime equal to minus PC loss equal to PC plus the capacitor power, because there is a ECS and other issues. So, for this reason real power required to be fed into the capacitor to maintain its receiver's voltage. So, thus 3 by 2 G D into I D minus the losses of the switches and the capacitor parasitics everything plus P C into V D C into I cap. So, I capacitor will be 1 by V D C 3 by 2 V G D into I D minus P C plus P C loss. So, from there what we can say is that the C B dB dt, this is basically nothing but a current C dB dt equal to 1 by V D C 3 by 2 V G D into I D minus P C plus the loss component of it, and previously we have neglected the loss component, here we have added to the loss component, otherwise you will find that DC bus voltage is sinking. So, dB dt equal to C part will come here, ultimately this is the expression, this is nothing but a ripple. The rate of change of DC bus voltage is nothing but a ripple. So, it is 3 by 2 CB GD VC ID minus 3 by 2 PC plus PC loss by GD. So, this will be the expressions of the ripple, and you generally design with a permissible limit, because you know that what is the power of the converter, what is the losses you should estimate or calculate, and you know the grid voltage. So, there is a problem, you know, if there is a voltage sag, the ripple will be more. So, for this reason we require to have a, please go back to the circuit, please go back to this controller, you have extra voltage control, DC voltage control loop if there is a voltage sag. So, this is the case, you have VDC star minus VDC you feed to the PI control, and this part is essentially the losses that you have this value, and then you subtract it, you add up, and within that you can have a ID max and ID min. Generally we calculate by we putting everything in a PI controller and try to do that. So, ultimately you left everything to the tuning of the PI controller, but it is a quite blind operation, and for this reason I suggest go by this way. And this is a physical system, this is a power flow, this is a voltage source converter, and there is a delay. For this it is incorporated by 1 by 1 plus equivalent switching of the timing, that will give you ID. Thereafter you got a VD, you got PC, this is a losses, ultimately you got a I cap into 1 by CS by U. So, this is a way of power flow in case of the DC part of this voltage source converter. So, let us recap what we have said. So, this is called the voltage droop control. Sometime it is very much useful, because this is a, once you find that voltage is drooping, that is applicable not only that power quality issues, but also in case of the distribution system, especially we are talking about DC microgrid, there these features are featured in a long way. So, PC minus PC star minus PC RDC minus VDC star minus V should be equal to 0. Then you say that you are maintaining a constant voltage. Now, this is the inverter mode and this is a rectifier mode, and you have a PC minus PC star PI equal to ID prime. Similarly, if you want a constant DC voltage control, you require to maintain the DC bus. So, you have, and we generally do that in case of the shunt active power filter. So, it is VDC star minus VDC, and from there you got a PI controller, that is ID. So, this is called a constant voltage control method, and sometime we maintain that, and sometime we go for the droop control. What happen, you have a inverter mode, their voltage goes up, and you got a rectifier mode, you generally power feed in, and thus you got a resistance of this RDG, and you require to operate in that mode, and this is the control of the power, and this is actual reference power of the converter, this is actual power of the converter, that will be the difference will be the E, that will be the fit into the system, that is the ID star. And direction of the ID star will depend on whether you are operating in a converter mode or the inverter mode, and you got IRDC. Thereafter you have VDC star minus VDC, and it will be divided rather by RD, and ultimately you will be calculating the value of the ID star. So, this kind of control is the dupe control method, and this is followed in a mainly DC microgrid kind of system, where power is flows through or take away through the front end active converter, but power quality plays an important role, because once you are taking power from the grid, you cannot throw the garbage into the system, and also once you are injecting power from your power surplus from the microgrid to the main grid, then also you require to inject also the quality power. So, let us see that this is a AC voltage control, and if distributed network is a weak network and the AC voltage has to be regulated by the voltage source controller, then instead of the grid it is a rigid body. So, we have to apply the KVL, and ultimately you have the current, that is basically your voltage by the apparent power. So, Vg will be given by the Vc plus this R plus j omega IL, and from there Vg will be Vc plus PR plus omega IL, because this part is required to be nullified. So, because we want that 0 reactive power to be supplied, and thus your grid voltage will be the change of the grid voltage will be omega L by Vg by Q. So, in that way injecting power to the reactive power will be injected. Since P is controlled separately, it cannot be controlled the Vg, that is the one of the problems. So, we know that in case of the we know that in frequency reactive power control comes from the excitation, and the real power control comes from the speed of the generator. Same thing here, since P is controlled separately, so it cannot control the Vg. So, it has to be controlled in a different mode. So, for this reason we require to have a frequency support of the AC microgrid. So, here we have a droop control, and thus we can control the frequency here, and in that way this is the reference current and this is the frequency droop control, and generally it is been used in the microgrid in detail. And frequency droop control with DC microgrid control, we can have this two coupled. This is the VDC, where DC bus voltage required to be maintained, and you have frequency droop, and both this will put into this place, and there is a PI controller, and this way this will be the ID reference. ID reference will stabilize both these drooping features. In that way voltage source converter also can be used for the mitigated for the frequency as well as the voltage drooping. Thank you for attention. I have almost covered everything, try to cover and get detail, that is the features of the voltage control converter, grid connected voltage control converter and its control. We shall look forward its applications in power qualities. Thank you.